Good morning everybody. So, today we will see different mechanisms of vapor formation, and in that connection we will also learn different types of nucleation. Now, vapor formation vapor formation, it has different routes. Basically, for vapor formation what is needed is that that there is a deviation from the equilibrium. So, vapor formation takes place from the liquid phase, vapor forms if there is a deviation from the equilibrium, and one can think of three types of deviation: deviation from stable equilibrium, deviation from metastable equilibrium, and finally, deviation from unstable equilibrium. So, let us examine case by case all these three different routes of vapor formation. Now, you see, first let us see deviation from stable equilibrium. So, suppose there is a planar interface, planar liquid vapor interface. Okay. This is a planar liquid vapor interface, and from the liquid we know that vapor can form. So, that means, this is your liquid and this is vapor, and from the liquid the vapor is forming. So, basically this transition from the liquid phase to the vapor phase is due to a deviation in the stable equilibrium condition. Vapor and liquid, they are coexisting together under stable equilibrium, and here only there is transition from the liquid to vapor. Now, one can think of another situation. Let us say there is a large pipe. Inside the large pipe there is flow of fluid, and this pipe is heated. At the periphery of this pipe there is heat input. So, what will be, what one can observe under certain operating condition, that there will be a liquid film adjacent to the pipe wall, and from the liquid film there will be evaporation. So, probably there could be a few droplets also, from there could be evaporation. Here also it is like this, that it is a deviation from stable equilibrium, though exactly it is not a planar surface. The second example, exactly it is not a planar surface, but if the pipeline, I mean pipe diameter is quite large. So, compared to that the film curvature that can be minimal, and here also the situation is quite similar as we have seen in the top diagram, where vaporization is taking place from a plain liquid surface. Now, in both these cases what happens, the condition for vaporization is that the surface temperature of the liquid should be only marginally higher compared to the saturation temperature corresponding to the pressure. So, at that condition only we will have the vaporization. And here the vaporization or evaporation process, basically it is called evaporation. So, this process, the mass exchange, and again what will be the heat transfer that is associated or that is related to the mass exchange, that can be obtained from the molecular flux, which goes from one phase to another phase. Okay. So, we will not discuss much regarding it, but let us know that there is one type of vapor formation where there is deviation from the stable equilibrium. Now, let us go to the second case. Deviation from the metastable equilibrium. Now, it is a very common experience that though the liquid temperature is above the saturation temperature, immediately vapor formation does not take place. In many situations, one can find that though the liquid temperature is above the saturation temperature, the evaporation or the vapor formation will not take place. Now, why it is so? If we have to explain it why it is so, then we have to go little bit into the mathematics part of it. You see, similar kind of equation we have derived earlier, but when we are forming the vapor, see, if there is a nucleus, vapor nucleus, and we have got some sort of a vapor embryo in the bulk of the liquid, then there is a pressure difference in the vapor phase and in the liquid phase, and this we have already derived. For a spherical vapor bubble or vapor embryo, it will be P v minus P L, the subscript they have got their usual meaning, that is 2 sigma by r star. This is our classical Young-Laplace equation. P v is the pressure in the vapor phase, P L is the pressure in the liquid phase, sigma is the surface tension, and r star is the radius of the vapor embryo. Now, you see, it is not a plane surface. So, if there is a curvature effect, some people have suggested some correction to this. So, this can be corrected something like this: P v minus P L is equal to 2 sigma by r star 1 plus V L by V v. So, V L represents the specific volume in the liquid phase, and V v that represents the specific volume in the vapor phase. So, if there is a cut surface, approximately one can have the difference of pressure between the two phases given by this particular formula. Now, you see, so one has to appreciate that the liquid and vapor, at least near the interface, they are very close to the saturation condition, and we can use Clausius-Clapeyron equation for this particular situation. So, if we use Clausius-Clapeyron equation, for this particular situation, so then what we get? So, this is our Clausius-Clapeyron equation. In some form we can write it. HLV is the latent heat of vaporization. Now, here one can make certain assumptions. One assumption is that specific volume of vapor, that is much higher compared to the specific volume of liquid, and also we can assume that the vapor that approximately behaves like an ideal gas. So, if we make these two assumptions, then the equation that can be simplified and probably that can be integrated also. So, one can have 1 by P dP that is equal to HLV m is the molecular weight of the particular fluid, R gas constant, R T square divided by R T square into dt, and then this can be integrated. So, if we integrate it from P L to P V, inside the vapor embryo pressure is higher. So, we can integrate it from P L to P V dP by P, that is equal to, again at the interface and at the liquid phase near the interface, the temperature is the saturation temperature, whereas temperature inside the vapor embryo is higher. So, we will get this particular thing. And one can do little bit of simplification. With simplification one can write normal log of 1 plus 2 sigma P L R star, this should be multiplied by 1 plus V L by V V. You see this last term is the addition this last term is the addition for or to take care of the curvature effect of the bubble. Now, generally this can be neglected also, this particular term can be neglected also as V L is much lower compared to V V. So, this is approximately equal to 1. Now, with all these approximation, and one can write T V minus T saturated, that is equal to delta T saturated, that is again equal to so, this is after making some approximation one can write this equation. So, what does this equation convey? This equation convey that if I have to make a vapor embryo of R star radius, then I need certain amount of superheat that is given by T V minus T sat, and of course, these fluid properties, it will depend on the fluid properties, whatever fluid properties I have given, the saturation temperature I have given. So, it will depend on that. So, I am getting a relationship that I need certain amount of degree of superheat for evaporating or for vapor formation, if a vapor embryo of radius r star is to be produced. Now, what is the relationship between delta T sat and R star? The lower the value of R star, the higher will be the value of delta T saturated. That means, suppose I have to make a small vapor embryo, I need to have a very large degree of superheat. Okay. Now, let us go back to some thermodynamics. I think let me draw this diagram so that it will be easier for you to draw it with me while I will explain. So, this is the conventional PV diagram, and we are interested in the two phase dome. We are interested in the two phase dome. So, basically in the PV plane for many common fluids, the two phase dome looks like this. So, here we are having critical point. Okay. Now, a normal isotherm in most of the textbook is represented like this. This is an isotherm. And here this isotherm temperature is constant, this is below the critical isotherm. So, this is a normal isotherm which is represented in most of the textbook. What are the different parts or different important important features of this diagram? So, this line up to K, this is the saturated liquid line and this is the saturated vapor line. On this side we have got subcooled liquid, on the other side we have got your superheated vapor, in between we are having a two phase mixture. Now, it shows that if we follow a isotherm, then as soon as it approaches the saturated liquid line, there is an abrupt change in the slope of this line, and again as soon as it approaches the saturated vapor line, vapor curve, then there is an abrupt change in its slope. Now, in many of the natural system or most of the natural system, this kind of abrupt changes are not very common. So, if this situation is conducive, then what happen? This curve will be a continuous curve with continuous slope, continuous change in slope, and the nature of the curve will be something like this. My drawing is little bit exaggerated, but this will be something like this. Now, what we can see that there are two extreme points in this curve. Now, the blue line which I have drawn towards the left side, this is called and the other blue line, broken line, that is called vapor spinodal. So, the idea is, suppose I am what I am doing, I am basically reducing the pressure here and I am following this curve. So, if I reduce the pressure, the curve will follow in this direction and then there will be a change in slope, and after that it follow the way I have shown it. Up to this portion, if there is minimum amount of disturbance, then it will continue to stay only in the liquid state. So, this is a metastable liquid state. On the other hand, on the right hand side of the curve, we will have a metastable vapor state. So, it will try to remain in the liquid state only, though the temperature here is the saturation temperature corresponding to the pressure. Now, what we can see, the temperature is remaining constant and pressure is reducing along this curve up to liquid spinodal. So, what does it mean? That here it is gaining certain amount of degree of superheat, because corresponding to this pressure the saturation temperature is lower, but it is remaining at a higher temperature. So, it is gaining certain amount of degree of superheat. Now, this degree of superheat is again related, as I have shown, to the radius of vapor embryo. As the degree of superheat is reducing, so corresponding radius of vapor embryo, that is also reducing. So, at some point it may come to the molecular dimension. Now, this is some sort of thermal agitation is always there in the metastable state of the liquid. Now, what will happen? There is a small but finite, this comes from the statistical thermodynamics, that there is a small but a finite probability that suddenly at this condition there will be a large number of vapor embryo in the bulk of the liquid and evaporation will take place, or some kind of nucleation, vapor nucleation will take place and process of vaporization will take place. So, this is called homogeneous nucleation. So, this particular phenomenon is known as homogeneous nucleation. It is not very common. It needs a large amount of degree of superheat, but it is possible, and it is possible only if the liquid stays at metastable state. So, then it indicates a deviation from the metastable equilibrium. So, we have got the this is homogeneous nucleation. Now, homogeneous nucleation, that can occur only in a very clean system, liquid is very clean, and let us say it is depressurized to a very high value, very suddenly it is depressurized, then we can think of, or one can come across a situation which is close to homogeneous nucleation. Actually, by if you make the calculation, you will find that homogeneous nucleation needs tremendous amount of energy. See, from the liquid, when vapor is forming, certain amount of energy is required, because an interface is to be created, and here small nucleuses are there. So, as the radius of a sphere that reduces, then the surface area increases. Okay. So, very large number of small nucleuses are there. So, very large number of energy is required. So, for homogeneous nucleation, a very large number of energy, large amount of energy is needed. That means, that can come from the degree of superheat. So, large degree of superheat is needed. So, it is not very easy to create this situation, but in some situation we can have this type of a phenomena. Okay. So, if I try to point out the difference between the if I try to point out the difference between the earlier process and this process, what is the difference? So, in the earlier process of evaporation, what we have seen that it is taking place from the plane surface of the liquid, then there is no nucleation process. Okay. So, interface, that is in stable equilibrium, for the two phases it is in stable equilibrium, no nucleus is formed. In case of homogeneous nucleation, we have got a bulk of liquid, and in the bulk of liquid very large number of, this is the bulk of the liquid, and in the bulk of the liquid very large number of nucleuses are formed. So, here one need to form certain nucleus for the vaporization process to proceed. Okay. So, that is the difference between these two processes what I have described, that homogeneous nucleation and your previous evaporation process. Now, as I have told that homogeneous nucleation is not very common. Commonly we cannot day to day phenomena, or let us say in industrial practice we rarely come across homogeneous nucleation. Then of course, I mean this is a process of vapor to liquid to vapor change. There could be a reverse process from vapor to liquid formation. So, there also situation close to homogeneous nucleation is possible, not always, again in some unusual or special situation, like you have the formation of fog. So, there also something close to, not exactly homogeneous nucleation, but something close to homogeneous nucleation, because very large number of liquid droplets, very small droplets are formed. Of course, there the system is not very clean. See, in atmosphere there could be large number of dust particle etc., but close to the phenomena which I am describing here is also present there, that very large number of nuclei are formed. Then most of the system, they are not very clean the way I have described, and most of the system are also not homogeneous, in the sense when I am describing the homogeneous nucleation, it is in the bulk of the fluid, but let us say the bulk of the fluid that has to be contained in something. So, there is a wall, solid wall. So, obviously, solid wall that breaks the homogeneity, the condition at the solid wall are different from that of the bulk of the fluid. So, homogeneous nucleation, as I have told, that it is difficult to get because of this reason, that we cannot also make the system totally homogeneous. So, then there is another kind of nucleation, that is called heterogeneous nucleation. So, heterogeneous nucleation, how heterogeneous nucleation will be there? Heterogeneous nucleation will be there because the bulk of the fluid, let us say water, water will have dissolved gas. So, it is having some sort of foreign material in it. There could be contaminants in the form of suspended material, suspended solid material, and then also there will be discontinuity at the wall. So, all these things, they gives rise to nucleus formation, and obviously these impurities or the surface irregularities, whatever I have described, they are not homogeneously distributed. So, the nucleus is now the nuclei will be not homogeneously distributed, and we can call this particular process as heterogeneous nucleation. And what has been seen from our day to day experience, as I have told, that if you calculate the energy requirement for homogeneous nucleation, it is tremendously high, but in case of heterogeneous nucleation you will find that it is not that high, it is quite low. Why it is so? Now, what we can see in heterogeneous nucleation, as I have told, the liquid is not that pure liquid. So, we can have, in case of heterogeneous nucleation, the liquid is a mixture of liquid plus gas. So, a very common example will be your water plus air. This is a very common example, that we will have a mixture of water and air in case of your day to day experience or in any industrial system. So, if it is air and water mixture, then our all the equations which we have used earlier, those equations are to be modified. How they are to be modified? See, the equation will be now P v plus P a minus P L, that is equal to twice sigma by r star. Okay. So, the partial pressure of air or any other dissolved gas in the liquid, that has to be considered also. That means, total pressure inside the vapor embryo minus the liquid pressure, that is balanced by your capillary force and comes from the basic Young-Laplace equation. And again what we can write is this: using Clausius-Clapeyron equation and following the previous derivation, one may write, we can write the following relationship: T v minus T sat, that is equal to R T sat T v. Actually, T v is close to T sat. So, in some expression one can have T sat square also, H L v m ln 1 plus within bracket this multiplied by again 1 plus V L by V v. So, this could be the relationship for the degree of superheat which is needed to create a vapor embryo. Okay. Now, here one can again make certain simplification, like V L by V v, that is very small. So, one can neglect it, and again one can neglect, suppose the quantity of dissolved gas is not much in the liquid. So, one can also neglect this quantity. Then one will left with logarithmic, natural logarithm of 1 plus 2 sigma by P L r star. Again, out of these two terms, this is much less than 1. So, one can expand this in logarithmic series, retain the first term. So, some simplification can be done. Now, what is the effect of the dissolved gas in the liquid? What is the effect of dissolved gas in the liquid? Can you identify the effect of dissolved gas in the liquid? If you simplify this, then probably it will be clear that the dissolved gas in the liquid, that reduces the requirement of degree of superheat. So, when there are there is a dissolved gas in the liquid, so you need lesser amount of or lesser value of degree of superheat to create the vapor embryo. So, that means the evaporation process that becomes more, that is dissolved gas make that process of evaporation more convenient. Even then, if you calculate what is the degree of superheat needed for evaporation to take place when there is certain amount of dissolved gas, you will be surprised to find that that is a still very high value, and our normal experience is that at a very small superheat, small degree of superheat, we are able to boil the liquid. Particularly, if you take the example of water and if you have some sort of a measurement device, let us say we have got a pan and the pan is over a heater. So, the pan is having liquid water, and we have got some method of measuring the surface temperature from where evaporation is taking place. So, mainly at the initial stage evaporation will take place from the surface. You will find the surface temperature at which the evaporation takes place, at which we can identify that the boiling process has started. The temperature is not very much different from the saturation temperature. That means, at atmospheric pressure the saturation temperature will be 100 degree Celsius, and probably at 100, 2, 3, 4 degree Celsius we will have the boiling from this surface. Whereas, the formula which I have given to you, you will find that with that if you try to calculate delta T sat, that is much higher. Now, where is the fallacy? The fallacy lies in the fact that dissolved gases, or for that matter the suspended particles, small suspended particles in the bulk of the liquid, though they help reducing the degree of superheat needed for boiling, they are not they do not play the main role for boiling when we are considering a system like this. Here the main role is played by the surface of the container. And if I see the surface of the container, whatever machining process I may adopt, whatever polishing process I may adopt, the surface is not regular surface. So, on the surface there will be surface irregularities. So, common metal surface we have irregularities. This we have discussed, but let us look into it in a bit detail. So, these irregularities are cracks, pores, crevices, etc. Okay. And they play a very major role in reducing the degree of superheat needed for boiling. How? We will not go into very detailed kind of mathematics, but we will try to give some sort of logic from the fundamental physics. Now, you see, as I have told that we are during the boiling process we are creating a new surface. We are creating a new surface. So, that is why some amount of energy is needed. Now, that energy if we can express that energy needed to create a vapor embryo, let us call it delta G, which is also a function of the radius of embryo radius. So, energy needed to create a vapor embryo is given by delta G, which is a function of r star. Now, this vapor embryo, we are assuming that this vapor embryo is formed in the bulk of the liquid. But let us say that there is a surface available on which this vapor embryo is forming, then what will happen? So, if there is a plane surface or flat surface available for the formation of vapor embryo, then this delta G R will reduce by a factor phi if a flat surface is available. If a flat surface is available, then this will reduce by a factor phi. Now, people have done again some sort of approximate analysis, and this phi can be calculated. This phi is given by 2 plus 2 cos theta plus cos theta sin square theta divided by 4, where theta is the angle of contact between the I mean it is a vaporization is taking place. So, on this particular solid surface, there is a triple line where or triple point where there is liquid, vapor and solid contact. So, at that point the contact angle that is given by theta. So, depending on the theta, we will have different values of phi. Now, let us consider different cases. Value of theta for different cases of solid liquid contact. Suppose the liquid completely wets the surface. Liquid wets the surface completely. So, what do you get? You get theta is equal to 0. So, if theta is equal to 0, from your equation what is the value of phi? Phi is equal to 1. So, the factor which could reduce the energy needed for the formation of vapor embryo, that factor is equal to 1. So, there is no reduction. So, delta G R, what I will calculate from the thermodynamics, this is your Gibbs energy. So, the same amount of energy will be needed. So, presence of flat surface is not helping me. Now, let us say the other situation. Liquid cannot wet the surface. Liquid cannot wet the surface. So, theta is equal to how much? Theta is equal to 180 degree and phi is equal to. So, if phi is equal to 0, then it is making the energy requirement 0 and it is also making the requirement of degree of superheat equal to 0. That can be shown that it will make the requirement of degree of superheat equal to 0. So, as soon as the saturation temperature is reached, we will have vaporization. Okay. So, in this case, as soon as the saturation temperature is reached, we will have the vaporization. In the first case, what we will find that, I mean, just like your homogeneous nucleation, whatever energy was needed for vapor embryo formation, the same amount of energy will be needed. In the second case, that we do not require any extra energy, we do not require our this one any degree of superheat. As soon as the saturation temperature is reached, our vapor embryo will form. Now, practical situation is in between these two. So, in practical situation, what will happen? In practical situation, theta value that will be from in most of the situations, so theta value will lie from theta will be within 0 to 90 degree. Generally, see, this is a range. So, it will be within that value. Then what will be the phi value? Phi will be within 1 to 0.5, 1 to 0.5. So, you can see that normally in normal case itself for solid liquid contact, we will have certain reduction in the energy needed for vaporization, certain reduction in the degree of superheat that we will get. Now, a drastic thing will happen because of the irregularities of the surfaces. If there are irregularities, these irregularities, I mean, a common way of describing these irregularities, that as if there are some conical pores inside the surface, I mean on the surface. See, basically the surface will look like this under a microscope. Now, if I want to idealize in these irregularities in a magnified manner, so it is like that you have got some sort of a conical aperture. So, you have got a conical aperture. This is the surface, inside the surface you have got a conical aperture. Okay. And the in this aperture you have got, this is the meniscus and this is the solid surface. So, the angle is something like this, this is your theta angle. So, this angle is now having a large value, this theta is now having a large value. So, for this large value what we will have, the factor phi will have a small value and we will reduce the degree of superheat. Okay. So, if there is a large value of theta, the way I have shown, then with a small degree of superheat, vaporization will take place from this spot, and this spot will now it will be called as a nucleation site, and we will call it as an activated nucleation site. So, there will be large number of sites like this, sizes are different, shapes are different, included angle, this angle if we call it, this angle if I call it beta, these included angles are different. So, at a particular degree of superheat, this site will be activated. If I increase the degree of superheat, another site will get activated. So, that is why when I start boiling, this I have explained other day also, when I have started boiling, I will see from the pan vapor bubble is rising only from a limited sites to start with. Then as the temperature is increasing, I will find that from more places the vapor bubbles are coming. So, more and more number of nucleation sites I am activating by increasing the temperature of the surface. So, that is what I am doing in day to day boiling, day to day phenomenon of boiling, that is what we are experiencing. And also in industrial situation, when on a tube or inside a tube boiling is taking place, the same phenomena is occurring there. So, we have got number of pits and those are actually nucleation sites. Depending on temperature, number of sites will get activated and we will have nucleation from there. Okay. So, this nucleation is called heterogeneous nucleation. So, you can understand why it is called heterogeneous nucleation. So, basically you see we have discussed three processes of vapor formation. First process, there is no nucleation and it is a surface phenomena. The second process, that is homogeneous nucleation, that is in the bulk of the liquid. Heterogeneous nucleation could be in the bulk of the liquid or it could be not on the free surface of the liquid, but on the solid surface, because solid surface contains large number of nucleation sites. Okay. And as nucleation sites are necessary, or rather formation of nucleation is necessary. So, degree of superheat should be higher in case of homogeneous and heterogeneous nucleation, whereas almost at the saturation temperature evaporation can take place. So, that is the difference between these three processes. Okay. Then now we can understand evaporation is important, but in this course we are not going to discuss evaporation, because that is not exactly two phase flow. One can separately discuss the two phases, the fluid mechanics and heat transfer aspect one can deal in a separate manner. Homogeneous nucleation, as I have told, that is not very important, because it occurs rarely. It is important in case of accident scenario, etc., in case of very high pressurization, depressurization of liquid, it is important, but we are not going to discuss that. But most of the boiling process are due to heterogeneous nucleation. So, we will start from here and next day we will see how does a bubble grow, how does a bubble detach from the surface, and then nucleate boiling. Okay. Thank you.